Now, something that's kind of connected to this idea is what's called the mean value theorem for integrals. We know the mean value theorem for derivatives, which is that on as long as a function's continuous and differentiable, on some closed interval, the instantaneous rate of change has to equal the average rate of change at least once within the interval. Well, the mean value theorem for integrals is kind of a similar idea. What it says is, as long as your function is continuous, somewhere between a and b, there's some c value, such that f of c, which is right here, is equal to the average value. So if this is the average value, average y value of this function on that interval, then at least once within the interval, the function itself has to obtain that average value. That's all it's saying. But the takeaway is still this, is that is the average value formula. That's still the big idea. Now, even though in this section we will refer to this as the mean value theorem for integrals, going forward, if I refer in the future to the mean value theorem, I'm still referring to the one with derivatives that we learned about last semester. So, let's do this problem. Example 3 says, find the average value of f of x equals 4 times x squared plus 1 over x squared on the interval from 1 to 3. So first we're going to find the average value, and then find all the values of x in the interval for which the function equals its average value. In other words, we're going to find what is guaranteed by the mean value theorem for integrals. So first we want to find the average value. So we're going to take 1 over b minus a, that would be 3 minus 1, times the integral from 1 to 3 of 4 x squared plus 1 over x squared dx. Once again, I'm going to turn to my calculator here, and you can as well, and we will get an answer. And it looks like we get about 5 1/3, which would be, what, 16 thirds? Well, that one we probably could have done by hand, just by distributing the 4 and then dividing by x squared. But whatever. On the calculator, we get 16 thirds. So that's the average value. If we go back here, I know the curve doesn't look like it, but that would be like saying that this is like the red line. That's the average y value of this function on the interval. But now we want to find the x, or c, in the interval that equals this. This is, right here, this is a y value. And we want to find what x value equals that. So we are going to take our function, 4 times x squared plus 1 over x squared, and we're going to set it equal to 16 thirds. I'm going to cross multiply. So 16 times x squared is just 16x squared equals 3 times 4 is 12 times the quantity x squared plus 1. So we get 16x squared equals 12x squared plus 12 if we distribute. Subtract the 12x squared, we get 4x squared equals 12. Divide, we get x squared equals 3. And x equals plus or minus the square root of 3. However, we're only looking at the interval between 1 and 3. So that would only be the x value of positive square root of 3. Negative square root of 3 is not within the interval. So that's the one spot within the interval where we attain the average y value. All right, moving on. This next problem, example 4, is more like an FRQ style problem. As a mug of hot chocolate cools, the temperature of the hot chocolate is modeled by a differentiable function h from 0 to 10, where time t is measured in minutes and temperature h of t is measured in degrees Celsius. Values of h of t at selected values of time t are shown in the table below. So we're given a table for the temperature of this hot chocolate at various times. The question says, using correct units, explain the meaning of 1/10 of the integral from 0 to 10 h of t dt in the context of this problem. Use a left Riemann sum with the 4 subintervals indicated by the table to estimate that value. All right, the first thing we should do is explain the meaning. Well, this is a common question, and when they have that fraction out in front, that should be a trigger to you to think average value, especially since that 10 down below is the same as the interval from 0 to 10. So the meaning of this would be the average temperature. We want to include units, so that would be in degrees Celsius from T equals 0 to T equals 10 minutes. That is going to be the meaning of that expression. And now we want to use a left Riemann sum to estimate it. So left Riemann sum, I'm going to look for the interval, the width of the first interval, which is 2, times the left endpoint, which is 66, plus the next interval has a width of 3 times its left endpoint, which is 60, plus the next interval has a width of 4 times its left endpoint, which is 52, plus the last interval has a width of 1 times its left endpoint, which is 44. 43 never gets used, it's only a right endpoint. I'm just going to type this in my calculator. And we get 564. Now, 564 is not our final answer. That is a Riemann sum approximation, and it is only an approximation for a definite integral. So it's only an approximation for that part of our expression. We need to now multiply by 1/10. So we need to take 1/10 times 564, and that gets us 56.4 degrees Celsius. That is the average temperature of this mug of hot chocolate over this time interval. At least it's our approximation for it using a left Riemann sum. Okay, example 5. This is the last problem. So we're given the velocity of a moving object, and its velocity function is t squared minus 13t plus 30 for t's greater than or equal to 0. We're asked to find the average velocity and the average acceleration on the interval from 0 to 8. And as you'll see, we're going to do this in 2 different ways. So there's really a couple different types of averages that we will have talked about in this class. One of them is today, and one of them we've talked about in the past. So first, we want to find the average velocity. Well, we're given the velocity function. Anytime you are asked to find the average of the very function you have, you're going to use the formula we've done today. So to find average velocity, we are just going to take 1 over b minus a, which is 8 minus 0, times the integral from 0 to 8 of our velocity function, t squared minus 13t plus 30 dt. I'm going to go ahead and do this one by hand, since we haven't done one by hand so far. So this is 1/8. I'm going to leave that 1/8 out in front of the bracket. My antiderivative would be 1/3 t cubed minus 13/2 t squared plus 20t. And we're going to evaluate that from 0 to 8. So we have 1/8 times 1/3 of 8 cubed minus 13/2 times 8 squared plus 20 times 8. Minus a bunch of zeros, and really all of that is being multiplied by 1/8. So I am going to turn to my calculator now. So 8 cubed divided by 3 minus and we end up with an answer that is negative 32 over 3. That's the average velocity. That's the average value of this velocity function. Now, the second question is asking for average acceleration. Well, if we had the acceleration function, we could do what we just did. But acceleration is really the derivative of velocity, or the rate of change of velocity. So to find the average acceleration, we don't really need to use this average value function at all. What we need to do is find an average rate of change. In other words, we need to take v of 8 minus v of 0 over 8 minus 0. In other words, we're finding slope. So v of 8 is negative 10 minus v of 0 is 30 divided by 8. That gets us negative 40 divided by 8, which is negative 5. So the average acceleration is negative 5. This is a different idea than finding average value, although two ideas are very much connected to each other, because v of 8 minus v of 0, this part right here, is fundamental theorem of calculus, the antiderivative values that we would get if we integrated acceleration from 0 to 8. We'd get the antiderivative value, velocity at 8 minus velocity at 0. The 8 minus 0 is the same as this 8 minus 0 over here. So in fact, the two ideas are related to one another. All right, well, that's it. Apologize if there's any errors. If you find any errors in the video, any mistakes I made, let me know. Otherwise, there is a worksheet that I will attach in Canvas that'll give some extra practice over this topic. Have a great day. Well, I already found one error. So on this problem here, I don't know if you noticed, but I wrote a 20 instead of 30t on the antiderivative right here. So the answer, with corrections, the answer should actually be negative 2/3 as the average velocity. Sorry about that. Bye.